Good morning, good afternoon, or good evening, depending on when you are looking or listening to us. And thank you for being in another episode of Material Business. Today is a very special day. I have a great speaker with every one of us, Dr. Fuad Khoshnaw. He holds a distinguished position as a senior academic and research at the Montfort University, DMU, in the United Kingdom, especially within the School of Engineering and Sustainable Development. He obtained his PhD in mechanical and manufacturing engineering from the Loughborough University in the UK in 2010. Dr. Hoshnaw's educational journey began with a metallurgical engineering degree. So he is another metallurgical engineer, just like myself. And then he did his master's and his PhD at the Technical University in Baghdad, Iraq. And then he was recognized as a Chevin Scholar, having successfully completed the business focus program on technology transfer and commercialization of innovation at the Centre of Scientific Enterprise Limited in London Business School in London. Then, from 2010 to 2016, he held the prestigious position of Professor and Dean of the Faculty of Engineering at the Khoja University in Iraq. In 2019, he served as a visiting professor of 2 months period at the Mons University in Belgium. In the most recent academic year, 2021-2022, he assumed the role of subject head of science, engineering, and computing at the DMU, Dubai campus. Dr. Khoshnaw has a remarkable publication record, having authored over 50 papers in prestigious international journals and conferences with high impact factors. Additionally, he served as editor of 6 books, showcasing his expertise and leadership in his field. His extensive research experience revolves around key areas such as corrosion, biomaterials, welding, failure analysis, and fracture mechanics. The contributions in these domains have significantly advanced our understanding and knowledge of these critical areas of study. Thank you for being here with every one of us.
Thank you very much, Ms. Monica Hernandez. It's my pleasure to be here with you and talking about corrosion, other topics about sustainability, fracture mechanics.
Absolutely. Sometimes we think those terms of sustainability are for other people, and the more we talk with experts around the globe, the more that we realize it's not the case. We also play a big role, a huge role, I will say, in all this transition, and what are we leaving for the next generations to come. So without further ado, you have addressed corrosion related challenges in your extensive research experiences and academic experiences. Could you share a real world case where the early detection of corrosion played a crucial role preventing maybe some kind of disaster or something unwanted, and how that tackles down the role of material selection?
Thank you very much. Thank you for inviting me for materials business session. I hope it will be useful for the audience. When we talk about corrosion, let's go back somehow to the principles of corrosion. It exists for all the time, everywhere, and there is no material has zero corrosion rate. So every material somehow corroding in some environments, but it depends on the corrosion rate, how fast it is. Also, we need to remember there are corrosion in a general way. We always consider it as a bad phenomenon. However, in some technologies, corrosion used as a beneficial aspect of phenomenon. For example, in batteries, in machining, they are using the same principles of corrosion. But when that's what, in this way, it is corrosion under control. But in the other way that we are talking about it today, it's corrosion when we have no accurate and precise control on it. This makes problems and makes failure. So when there is corrosion with no control, or not completely there is control, also there is not absolute or 100% effect of corrosion on the failures. Most of the time, this corrosion combined with other factors, mainly mechanical, can be heat, temperature, and also can be, recently, we have become familiar with the biological aspects as well. So all these will combine. That's one of the reasons why corrosion topic is complicated, because there are different types of corrosion. That's one. And they are combined with other factors, not alone. So it is not only chemical action, can be mechanical and others. And can be also, as I said, the other reason that's making corrosion is not very straightforward understanding. It is not always going in linear way. So there is not always going, when the concentration is going higher, that means the corrosion rate will become higher. Sometimes the opposite will become right. So this unlinearity, let's say, of the phenomenon of corrosion makes things more complicated to be understandable for everyone. That's just a little introduction about corrosion in general. Coming back to your question, yes, there are always the early stage failure detection, either by that's can be the corrosion is the main factor or can be combined with other. There are so many well-known disasters happen due to failures in very high level or in around us. Daily life happens in industries and companies. So for example, Titanic in the long term, Discovery Space Shuttle, and the one in the Gulf of Mexico, the Deepwater Horizon oil gas. These similar disasters as well caused big problems, either causing huge human life lost. Scientists also, like in Discovery, they lost their life. Also has had a big impact on the environment, caused on the seawater, on animals, and the air pollution as well. So detection, the early stage failures help a lot to detect and to prevent these disasters for in a huge level. And when we talk about this, about early stage, we need to consider there is another point associated with the early stage detection failures, which is in the beginning, during design, material selection has a big impact on to avoid this failure. So as I said, for example, Titanic, let's take this as an example. The main reason that was belonged to the material selection, because the material that has been used, it was high strength for shipbuilding. There is no problem with that. The only thing that was at that time wasn't very clear that some materials, especially steel alloys, will be brittle in very low temperature, like minus 30 degrees centigrade. So when it's hit there's an impact load, suddenly hits a ice stone, for example, the absorption, the energy absorption will be very low, so it becomes apart. So this material selection is the first step to avoid these failures in the service life.
Absolutely. And I cannot agree with you more. And we have said it with other panelists that have come to the podcast as well, is we can determine the impact of any design, any product, any service at the design stage, almost at a rate of 70 or 80%. So we can know how much harm are we going to do in the long term after service life at the design stage. So that's something absolutely true that we have to, and it's a very powerful tool that we have as engineers, designers. It's something that is readily available. We have done it for years, so we just need to do it in the right way.
Exactly. Agree.
So yeah, absolutely. So you talked about in your books and lectures and investigations you have done. You talked a lot about mechanical failures, so like fatigue, creep, and then how those. And you just gave us an example on how that can lead to catastrophic failures. Besides that, what has some of the investigations that you have done concluded on identifying the root cause of those failures, and then what can be some of the measures that we implement so we don't fail as much?
Yes. Well, let's focus on these two, which are somehow most of the time associated with corrosion as well, especially fatigue. So fatigue is everywhere, same as corrosion. So very difficult to find out a component or an item that's not under cyclic load. So forever it is under one static level of stress. Very difficult to find. So all scientists and researchers, they agree that most of the failures around us, not necessarily as a first factor, but somehow fatigue is involved with around more than 90% of the whole failures around us. So fatigue has a major impact on failures. Sometimes it is pure mechanical cyclic stress. So the fatigue strength becomes lower than the applied stress. So that's fatigue, pure fatigue. And also sometimes associated with the environment, wet environment or chemical solution or temperature. So this combination between corrosion, fatigue, and temperature cause faster possibilities to fail. So to prevent that, we design it. That's called design. Shaft or any other mechanical components. In design, we need to consider two main factors. And that's also in every type of mechanical aspects of corrosion, not necessarily with only fatigue. We have two sides, applied, which is external factors, and these external factors can be stress, can be temperature, can be ions, chemical solutions, or any other external factor. So that's in one side. On the other hand, we have the strength of material. So in very simple way, design means that the strength of the component must be higher than the external applied factors or external load. So when the strength of material is higher than the applied load, then it is safe. In general, we call it safe. However, where is the problem? Because in every design we do, designers, they do, we follow this principle. We calculate that the applied load or the applied stress is lower than the strength of the material. So where is the problem then? Why fail happens? The fail happens because there are some uncertainties in different aspects in load. So when we say the applied load is this amount, it is not necessary this applied load will remain in this level forever. Sometimes it's going up. So there is uncertainty. On the other hand, when we say the material has this strength, so the yield strength of this material is, let's say, 300 megapascal, not necessary that's always remain in this. For some reason, for example, when it is going to high temperature, the yield will become lower. And as I said just now about Titanic, we always try to consider the high temperature, but low temperature has a negative impact in some applications.
Mm-hmm.
So these uncertainties needs to be considered in design. Welding is another aspect that when we put welding, when we see that the component has welded items, that needs to be, because with welding, the microstructure will be changed. When the microstructure change, the mechanical properties of the material also will be changed, maybe in a better way or maybe not. So this needs to be considered in the right direction. For example, in duplex stainless steel, which is two phases, ferrite and austenite, in certain temperatures, there are specific phases. For example, sigma phase, chi phase will be created inside the material, and this has negative impacts on the mechanical properties, especially on corrosion and toughness. So during welding, these phases might be generated inside the material, but we haven't considered that during design, because we only consider the quantitative aspects, not qualitative. How the microstructure, when it is changing, its effect on the fatigue strength, the yield strength. Mm-hmm. So all this design, it's about taking consideration and be aware of all the uncertainties about considering all the uncertainties about during design aspects. For example, another example that needs to be considered, the size. In some components, or for example, let's say toughness. Usually we understand that when the thickness of the material is becoming larger, the cross section, that means the strength of material becomes at least the same. But for toughness, increasing the cross section will lead to reduce the toughness, because the possibility of having more defects in the larger cross section is high. So what I mean here by taking all the uncertainties about different aspects, quantitative, qualitative, if the designer can consider all these, then the component will be safe last for long. Otherwise, if one of these aspects have not been considered in design, this is all will lead to, let's say, early failure that was happened. It's happened before the expected time life. So,
And that, it is absolutely truth. I mean, it is the aspects that we need to consider are all of them, like you said, quantitative, qualitative, morphology, what could happen if we weld, what could happen if we don't do post-weld heat treatment, what could happen if they change in operation cycles, if the component was designed. For example, we have a lot of beads here, and then they were designed for sweet service. And then now we are discovering that the more they dig, the more sourness we add into the equation. And that wasn't the case when we designed, because we had set parameters for the wells to be sweet instead of sour. So now we have a whole bunch of reassessment to be done downstream to try to calculate how can we check for those failures that were not designed previously for. So absolutely is we need to take in consideration not only normal operation but also offset cases as well.
exactly. Yes.
Yeah.
Yeah.
Yeah, incredible. So how all these things, mechanical failure, material selection, when we talk about sustainability, and now that you are very close, it is close to home, this subject, how we can tie that up? We know that obviously if it doesn't fail, then we don't produce all the bioproducts and external things that corrosion or failure comes with, and then we obviously don't degrade and we don't hurt people, we don't hurt the environment. Most importantly, we don't produce waste unnecessarily. So how can all those things um, get together in the world, in the big world of sustainability?
Yeah. Um, well, for every failure, we can imagine when any failure happens, especially in big plants, big companies, and especially where the products of that company related somehow to other um, products will bring some consequences with it. So there are so many scenarios we can make how when a failure happens in one of the industry, what are the consequences will bring to other to the environment, to the human life, to economy, cost, all these things. And this will be more highlighted when the failure is unexpected. So it is early stage failure. When we expect that for example, turbine blade will last for 20 years, but crack happens in 2 years. This is unexpected, will bring so many consequences to the other industries and people around. So when, for example, if the turbine blade is for producing electricity, let's say, when this is shut down for this reason, that for unexpected failure in early stage, then some other companies will rely on this electricity. So they will be also shutting down, or the production will be less. And this will affect on the cost, on the delivery of the customers, and so many other this might cause legal consequences because of the delivery is late, and maybe also will be linked with the insurance, with penalties and so on. All these things belong to because unexpected failure happen in early stage. So there are ways of that. And to avoid that, on the other hand, when we have coming back to design and design for sustainable materials, when we improve the components, then durability of the product will increase, will reduce the early failures, will expand or increase the product lifespan, and enhancing the customer satisfaction about this, about the product, about the company, and also somehow we can link it with the environmental impact as well and cost savings. So there are different scenarios we can make about each failure when we know the specific, what's the specific outcome or the product, type of product of the company, how is that affect on people, about the cost, about the environment, and the government also maybe will somehow will be affected by this. So to avoid that, there are some advices, there are some procedures we can, a part of the design we mentioned just now. So there is like laboratory works, research, making proper prototype and testing before going to the actual production of the component, analyzing using modeling and simulation. These are before putting them in the market, so production stage. And when the material becomes in service, then inspection, periodic inspection in different ways. That will help to avoid any sudden failures. So, for example, I had a student worked on one of the like turbine blades cracked much earlier than the expected lifetime. So like 20% of cracked happened in 20% of expected life, which is for some reason maybe we concluded that it was because of the operational inappropriate operational conditions. So this, when crack happens, when we see crack on somewhere, as long as the loads or the stress or the conditional operations were enough to cause initiation the crack, then we need to consider this crack will propagate, no way, and will propagate to fracture. So as long as we see the crack, we need to somehow to stop if possible, or to start at least to replace, because this crack will propagate definitely unless there is a chance to reduce the load. But if it is going on the same load, on the same stress that the crack was initiated by it, then it is not safe to continue with that level of stress. So, as I said, there are so many scenarios. Depends on the product, the company, the industry, how this can impact on the cost, on the environment, and the government.
Absolutely. And everything makes so much sense. It is when we do the risk assessments, then we determine what could go wrong. But normally, when we do that, we do it with certain parameters in mind. What I'm hearing that you're saying, and what I have been saying too, is we have already tools that can help us simulate what could happen if. So the what if scenarios. So what if the load is not that? What if the load is that? What if we cannot get the temperature under control? What if the operator doesn't open the valve? What if? So all those, and we will check on those aspects when we do HACCPs and LOPAs and all those exercises in production sites. But it is at the design stage we could add some more of those kind of tools that we have already in hand, and will enhance the life cycle assessment for that particular element or part or component or whole equipment. So it is nothing that we don't know or we don't have. It's nothing that we have invented or we don't know how to do. We have it. It's in our hands. We just need to use it for our benefit.
Exactly. When, as you said, the corrosion and failure analysis is transdisciplinary concept. So as teamwork always is good, everyone will cover part of it to understand, to realize the expected failures might happen. And this can be considered during design, during material selection, manufacturing, and environmental aspects. All these, when it is combined, then sustainable design can be achieved.
For sure, absolutely. And I think we'll have some of that. Like we are getting more and more aware of that aspect. And I have said it many times: is we have the tools in hand. We don't have to invent anything. We just have to use what we have in hand at the right moment, so we don't get surprises when we don't need to. So, talking about all these, and I know some people will argue that then how much engineering time will add or how much will put extra into that stage to make it sustainable. So what do you think is the balance? Because you have worked a lot on that. So what do you think is the balance, or can you give us an example maybe of any time that you have achieved this balance by introducing design modifications, but then getting improvements in the process?
Yeah. Well, about this balance, I think the best example can be car industry or any transportation means, airplane, trains, where there is, on one hand, we need lightweight to save energy. But at the same time, we need high strength and durable components. So this balance for engineers is always the challenge. Using fuel instead of the cost, that also has a big impact on the environment. So always trying to reduce the amount of the fuel. And reducing the amount of fuel can be done as a direct concept by reducing the weight of the components, for example, using less density material in manufacturing these components. This can be done through using different technologies for example, nowadays we are 3D printing is very common to use different materials for specific shapes. So that's one, or can be done through, for example, different materials that have high strength, but at the same time has low density. Also manufacturing process using specific types of coatings, for example, nanotechnology, putting other elements, alloying, or foam technology, cellular structures. All these types of new technologies that are uh, associated with high strength of the material but low weight somehow can make this balance happen. However, these things are still under research and needs to be improved. But that's the concept of how this balance can be achieved. So, for example, if we bring it back to the failure, we said that welding, one of the reasons that accelerate failures in many components. But if the designer try to replace welding by other technologies, for example, 3D printing, and considering all the metallurgical aspects that associate with this remelting process, that somehow can improve the product and bringing the required strength for the material. Other way that if it is complicated shape, for example, if we don't want to remelt the material due to this change of the microstructure, there are other aspects of, let's say, powder technology, where the material still not be melted, but will take the shape. So this type of things about manufacturing and selection of material and the way of processing, these ways can make can lead somehow to get the right material with certain level of strength, but at the same time it is with low density or lightweight.
That's a great example. And yeah, the aviation industry, the car industry, they have to be creative. And then because they have to make the balance between many aspects, and it is really right at the design stage and the manufacturing where they can be exploring all that creativity, and then seek, like you said, 3D printing. And we had one panelist, and she's from UAE, and one of the main products of her company is car parts. So I immediately made the connection. So becoming more creative, but also having the right person in the team is what I hear that is key component of this process for it to work. So we need to have people that understand, and then multiple disciplines like you referred to before, so we can bring ideas, and then the more diverse team. So we are talking about all the sustainable development goals here, having diversity on the table, bringing new ideas, collaboration, and then making things sustained in the long run by looking at what could be wrong before it gets to that point.
That's the target, exactly.
Yeah. I mean, our discussion is super interesting. We are almost at the end of the time here. Do you have any message for the audience that is listening to us?
Well, it's all about these days, all the world suffering from the depletion of resources, and these resources can be metal, ores, or water, or air, clean air. So all these have led to think about sustainability has become very active at the moment. How we should use the material to last for long and not affecting the environment in the bad way. So this is all about coming back to which type of material we need to use, how do you use it, which technology can be used in the least amount of material to cover the requirement, and how to design. All these will lead to have a sustainable material or to be used in a sustainable way. To reach that point, work team, multidisciplinary works, research are necessary to be done. So it's difficult for one person to cover all these aspects from biological, environment, mechanical, corrosion, material selection, difficult. So it is always good to have, to give it a proper time to link it with other sections as well, or sectors. For example, government, NGOs, companies, all these to be involved to achieve this sustainability, which is SDG 17, which is partnership. That's important to be always on the table. Not only universities or academics or industries can be linked, other aspects. At that time, then proper regulations needs to be taken place to guarantee that the sustainability and the protection of resources will be achieved.
Absolutely. I could have not closed it in a better way. You have done it perfect. We need all to be together in this, and we need to pull the little chart in the same way. Otherwise, we won't be successful at doing what we are supposed to be doing. Thank you very much for coming into the podcast. It was a real pleasure to have you with us today. And I hope we'll have another opportunity to keep on discussing and then sharing many things. And yeah, thank you so much, Dr. Khoshnaw, for being here.
It's my pleasure. Thank you very much. Yes, sure. We will continue.
For sure. Thank you so much for the audience for always being here. And I say to you, stay tuned. We'll have another panelist in a couple of weeks. And with that, I say goodbye. And my name is Monica Hernandez, who's host for the Material Business Podcast with Infinity Growth. Thank you.